Hi AP Chemistry students, we're going to be talking about calorimetry tonight. And in calorimetry, we are talking about the measure of heat flow. That's really what's happening here in calorimetry. And we'll be talking about things like calorimeters and especially coffee cup calorimeters. So calorimeters is just going to be an apparatus that we're going to use to measure heat flow. And the easiest type of calorimeter that we see is this coffee cup calorimeter right here. So let's talk about that real quickly here. So again, in calorimetry, we're trying to measure heat flow. And so what we can do is we can just take some styrofoam coffee cups here. We usually get a couple of them and we put them inside of each other just to give us that extra insulation that styrofoam does provide. And then inside here, and we can't really see it, we can do a couple things. One, we could put some liquid in here, maybe just some water if we wanted to. And we could add, and we take the temperature of it using our thermometer here. We have a glass stirrer and maybe a cork stopper to keep heat inside of this. And if we wanted to, we could open this guy up and add into it maybe some metal or something like that. That's at a different temperature, and that would cause the heat to be transferred from the metal into the water, and then we could measure that temperature change. It's one way we could go about this. Another way we can go about this is because we have, let me erase this real quickly here, because we have a nice little system that we are hopefully not going to lose too much heat to the environment. We could maybe pour a couple solutions in here. Let's say we poured in some sodium hydroxide solution and maybe some hydrochloric acid solution. And we could have a neutralization reaction occurring, which would, and we could find out if that's exothermic or endothermic. Would it be giving off heat to the environment, or would be okay, so those two examples are just a couple of the ways problems might get thrown to us. Let's talk about a few other things. Let's talk about specific heat capacity here, specific heat capacity. And we also call this, just for short, specific heat. And we'll also use the capital C as our symbol for specific heat. Occasionally you'll see maybe in some other textbooks they use a lowercase s. But the specific heat capacity of any substance is the amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. And so different substances take more energy to raise the temperature than other substances. Some substances heat up very quickly, some substances heat up very slowly. And so let's talk about the formula that we're going to use with specific heat capacity. And that's this formula here, Q equals mc delta T, and you probably remember seeing this one in general chemistry. We're just going to review it real fast. We can also use for this Q delta H, which is enthalpy. We kind of use those interchangeably depending on if pressure is constant or not. But Q is going to be our heats. Delta H means heat as well as constant pressure, which is our enthalpy, measured in joules or sometimes measured in kilojoules. And remember, if we do ever need to do we go from one thing to another, 1 kilojoule is equal to 1,000 joules. So if we ever need to transfer back and forth on that, we can. In this formula, M is going to be mass, measured in grams typically, sometimes kilograms that we've got to convert. Specific heat in this formula is going to be measured in joules over grams multiplied by degrees Celsius. That's our unit for specific heat. And again, that's the amount of heat needed to raise the temperature of 1 gram of substance by 1 degree Celsius. And then delta T, delta meaning change. And so this is going to be a change in temperature degrees Celsius, or in Kelvin sometimes as well. It really depends. It's a magnitude deal, so we don't have to worry about doing any conversions between those two. But we'll kind of keep everything here in Celsius, hopefully. Just a couple of other brief things that we should talk about here. And water has a very high specific heat here, 4.18 joules over grams times degrees Celsius, meaning water is going to heat up very slowly and it's going to cool down very slowly, which is why coastal cities that we ever visit, Santa Cruz or Pismo, all have very mild climates, whereas here in the valley, temperatures fluctuate rapidly, where we get 105 degree summer and maybe a 30-degree winter, so because we don't have a whole lot of water around us. Whereas in Santa Cruz or Pismo, maybe it's going to be 65 year-round, very nice. nice. Aluminum would be having a very low specific heat capacity. Specific heat 0.9 is relatively low, not as low as some other things though, but aluminum heats up and cools down really fast. And so that's the difference between those two values. You probably will need to know, I believe this one's given to us on our equation sheet. The aluminum's not, but it's not something we need to really commit to memory. It's usually given to us in problems. So let's look at a sample problem or two, and then we'll give you some problems for tonight. So sample problem number 1, it says how much heat is needed to warm 500 grams of water from 22 to 98 degrees Celsius. So what we're going to do is we're going to use Q equals M multiplied by C multiplied by delta T here, and then plug some values in. And because we are dealing with water, again, C, that specific heat, is going to be 4.18 joules over grams times degrees Celsius as our unit. So let's throw some things in here. So Q is equal to mass, which is going to be 500 grams, multiplied by specific heat, 4.18 joules over grams times degrees Celsius, multiplied by our delta T value is going to be our change, and so we're just going to subtract those two. And so 98, 22, so I get 76 degrees Celsius. And then it just becomes a simple multiplication problem times 4.18 multiplied by 500. And so I'm getting a relatively large answer. Looking at units, grams is going to cancel and degrees Celsius is going to cancel. We're going to left answer with joules. And so I'm getting 158,840 joules, way too many sig figs. So we could round this off and call this let's call it 1.59 times 10 to the 5th joules, or if we could also convert it to kilojoules if we needed to. Okay, let's go down here to another sample problem here, and it says how many grams of water would require 2.2 times 10 to the second joules of heat to raise the temperature 34 to 100. Remember specific heat of water. Okay, so again, we're going to say, sorry about that. That was a little mistake. I'm not sure what I'm making there, but let's try this again. How about we go Q equals MC delta T, and it looks like in this case we're solving for mass, so we're going to make it mass is equal to heat over specific heat multiplied by delta T, change in temperature, so we can plug in some values here. Q is heat, 2.2 times 10 to the second joules, all over C for water, which is going to be 4.18 joules grams times degrees Celsius multiplied by delta T, which is looking like delta T is right at about, we'll call it 66 degrees Celsius, and Celsius cancels, joules cancels, we're left with the answer grams. And so let's get this punched through our calculator here. Okay, so the answer I get is actually a relatively small number here, 0.797. So really, not really a whole lot of water being heated up by the addition of really only 220 joules, 2.2 times 10 to the second. So that's going to be the last problem for tonight, and then there's going to be an attached worksheet or a PDF for you guys to do some problems off of. Hope you have a good evening.